Thank you. Okay, we're happy to welcome Niel de Beaudrap here today to talk about simple ZX and ZH calculi for arbitrary finite dimensions via discrete integrals. Please take it away.
All right, thank you very much. Thanks for the opportunity to talk about this. So the title is accurate, but there's more to this topic than that. It just is difficult to describe in summary all the things that we're doing here. But I'll describe in summary what it is that we aim to do with this. And the discrete integrals is where we started with this, and I think perhaps one of the most important components. Okay, so ZX and ZH, of course, this audience knows them very well. And the standard interpretation of ZX and ZH diagrams on qubits specifically are along these lines, where you just have a sum over either a standard basis or a conjugate basis. You have a phase parameter, which defines an angle parameter that defines a relative phase in between the two terms. And then also you have the Hadamard, depending on how much of a purist you are. It's not strictly necessary, but it's often useful just conventionally to explicitly recognize this as a generator. And then for ZH, we have instead emphasis specifically on the standard basis. The white dots are very similar to the green dots in the ZX calculus. We have these H boxes, which are denoted here by yellow boxes, which expressed as matrices look like this, a matrix consisting entirely of ones except for one coefficient, which is an amplitude, which parameterizes the H box. And we have gray dots, which we think of as imposing parity relations in between the various indices, parity relations computed, again, with respect to the indices of the standard basis. And we have a not dot, which simply represents the not. In the original work on the ZH calculus, the right-hand two ZH diagrams are described as derived generators. In this work, for technical but uninteresting reasons, we prefer to think of them as primitive generators. This will help us to describe how we can interpret them under different sorts of semantics for these calculi. By the way, if there are any questions at any point, please feel free to interrupt. Now, one feature, if you like, of ZH and ZX diagrams under the standard semantics, that is to say, the semantics with which they were originally defined and or almost always described, is that for many frequent diagrams, such as, for example, to represent the controlled knot, or for many different rewrites that one frequency sees in practice, you have scalar gadgets arising. And this is something which we're actually fairly familiar with for those of us who like to consider scalar exact transformations that represent semantics being preserved with equality rather than proportionality. And so here are some standard ZX rules on the left. Here are some subdiagrams whose only role is to represent normalizing factors in order to make the equality hold. And these are what I will refer to as scalar gadgets. They are simply subdiagrams, closed subdiagrams, whose purpose is to denote a scalar. And then not just in the rewrites, but the very most common, I would say, practically speaking, source of such scalar gadgets is in representations of something such as the C-naught. This diagram in the upper right denotes the control knot operation. Without that scalar gadget, that's not true under the usual semantics for the ZX calculus. And then, it's no different for ZH diagrams. One nice feature of ZH is that you can denote scalar diagrams much more transparently. So these isolated degree zero boxes denoted, labeled by 2, parameterized by 2, represents precisely the scalar 2, which I would describe as a very good feature of ZH generally. But the fact that for rewrites such as a bialgebra law or a fusion law of H boxes, it's unfortunate that non-trivial scalar gadgets arise. But it's unavoidable for the standard semantics for ZX and ZH diagrams. Now, in order to try to address this, back in 2020, I tried to describe an alternative semantics for ZX and ZH diagrams that would, by doing some fine-tuning of the semantics, allow us to dispense with these scalar gadgets. So in particular, there is a semantics for these diagrams, which is closely related to the standard semantics, for which these are instead the correct rewrites, or for example, the correct denotation for the control NOT gate. Simplified simply by removing these extra scalar gadgets, which become unnecessary. In the case of the ZX diagrams, actually under the so-called well-tempered semantics, which is the name that I gave this, those scalar gadgets actually end up representing the scalar 1 as they stand. And so you don't actually have to explicitly denote them. They're not engineered specifically to, or not with the express purpose of making those specific gadgets equal to the scalar 1, but that's a feature of these semantics, and you can think of this as partly why we can dispense with those particular scalar gadgets. In the case of the ZH calculus, I do not attempt to make 2 equal to 1 in that work. It's simply the case that under the different semantics, these are the rewrites that are sound. Okay, so under these semantics, we get rewrite rules such as these. So here's a sampling of the rewrite rules for the well-tempered ZX calculus. That is to say, the ZX calculus with well-tempered semantics. You can see the only one that involves any scalar at all is the so-called Euler rule. These, by the way, are generalizing rewrites, or rather they're analogs of rewrites described by Wilmert for a nearly minimal formulation of the ZX calculus. The Euler rule there follows more or less his Euler rule. There's a slight difference in the representation for the angles. That's a technical detail that's not very interesting to us here. But the scalar gadget there just simply serves to denote an actual phase factor of e to the I gamma. So we can't dispense entirely with scalar gadgets, but we can get rid of most of them. And there's some additional rewrite rules, very simple ones to rewrite to manage which scalars do arise. And following Wilmert, from which these rules were derived more or less, these set of rewrites are complete. This is all over qubits still, I should mention. For the ZH calculus, these are the corresponding rules that we get. And again, we don't entirely avoid scalar gadgets. Note in particular the so-called ortho and average rewrite rules. We have scalar gadgets for the square root of 2. Similarly, on the sort of mid right-hand side, this rewrite spec Z, this is representing the fact that the calculus is not special, but quasi-special. If you take 2 white nodes and you connect them by multiple edges, you get non-trivial scalar factors. This is perhaps a sacrifice you might say is worthwhile to make. This could be a matter of opinion, or perhaps a matter of application. It depends on how you wish to use the ZH calculus and which rewrite rules you find frequently occurring. For the sorts of rewrites that I find myself encountering, thinking about quantum computation or other applications of ZH to represent tensor networks, I don't find myself frequently encountering a rule such as special Z, while having a fusion rule for Hadamard gates, which do not involve scalar factors, or for a bialgebra rule, such as bialg ZH on the right-hand side. For those not to have scalar factors is, I think, a very nice feature. This is, again, derived from rewrite rules from the original presentation by Alex and Miriam. And again, these rewrite rules are complete following them. The completeness of this calculus follows as a derivation from their proof of completeness. Now, all of this change of semantics, what is this change of semantics? What was done in order to make these rewrites sound? So if you might think that it's very nice to have simpler rewrite rules, but you also have to explain how you come about the semantics to make those rewrites sound, and not necessarily the process by which you discovered how to do it, but just how you even express those semantics. In practice, this involved a scalar, which I described as nu. It's 1 over the 4th power of 2. Sorry, 1 over 2 to the 1/4, 1 over the 4th root of 2. You might wonder where this comes from, and well, may you ask. It's possible to derive it, and there are some hand-wavy arguments you can give for why you might expect to do that, but it takes a little bit of humming and hawing to describe it. But having isolated that scalar, this is how you might define the green and red nodes, the semantics for them, in order to come up with these well-tempered semantics. They're very similar to the standard semantics, but the entire operator is prefaced by a scalar factor of, well, some power of nu, which depends on the total arity of the dot. And it's not a super complicated formula, but it's not as simple as you might hope. Certainly not as simple as the standard semantics to express. For the ZH calculus, you have similar issues. The not dot remains simple enough. There's no problem there. For the white and the gray nodes, you have similar powers of 2, but acting in opposite directions, if you will. The scalar factors that you apply are inverses to each other. And the H boxes involve another related scalar factor, but which is different from either the ones that you would apply either for the white or the gray. Here I also have relations to the red and the green nodes in order to describe how this allows you to relate the ZH and the ZX calculus together to make it one interoperable system of nodes, and you don't have to be too concerned about which precisely are your primitive generators, but that would allow you to manipulate mixed type diagrams. Now, they're different by the semantics, by the standard semantics, by powers of a single scalar, and that those powers depend only on the degree of the dots and the boxes involved, the primitive generators of the ZX and the ZH calculi. So it's not terrible, but it's a bit awkward. It is admittedly difficult to describe why you would want these precise things. There are reasons for it, but there is no sort of a priori explanation for why you would choose these in particular. Now, moving on to qudits with the ZX and the ZH calculi. Of course, there's more work to be done if we want to come up with useful and versatile systems for qudits. There's already some people who've done some good work on qudits or for qudits of odd prime dimension in general. But what can we say for arbitrary dimension? That's something that might be useful to do. And in particular, I'm very fond of the case of a qudit whose dimension is a power of 2, not because this is something that we would expect to use as a substrate in a physical system, but because this allows us to reason about such things as operations on registers, which denote integers modulo 2 to the d, which is what we would most naturally do with sort of a straightforward translations of Shor's algorithm into qubits. We would group the qubits into logical qudits of dimension some power of 2, rather than just 2 itself. And so I'm very interested not just in prime dimension, not just in odd dimension, but in what can be done in arbitrary dimension, and at the very least, what can be done for powers of 2. So we will have the same problem as we had for qubits, involving scalar gadgets. They're simply going to arise if we take the most straightforward definition of the generators. And of course, for arbitrary dimensions, there's a reason why this isn't done and dusted decades ago. It's because things get a little bit awkward. There's all sort of fiddly considerations that you have to deal with. So for example, the most obvious case is, what if the dimension is composite? In which case, well, a lot of the things that we like to reason about, we'd like to think of the index labels for the basis of our qubits to represent something like integers modulo d. Now, the integers modulo d, if d is composite, is still a perfectly nice thing, but it's not a field. And that means that you can have zero divisors, that is to say, pairs of non-zero entries that multiply together to give 0. And that makes your analysis more complicated if you can't assume that every element of your index set has a sort of multiplicative inverse. There's even worse. What if your dimension happens to be even? There's all sorts of awkwardness that arise with even dimension. We can see this even with qubits. We're used to working with the qubit case simply because it's the most primitive case in a manner of speaking, just the number of dimensions. There's a heavy bias towards it for very good practical reasons, for trying to work with quantum technologies where we expect there's, it's not a given, but there's a very strong chance that the basis of quantum computation on the hardware level will be qubits rather than qudits of any other dimension. So we are somewhat inured to the weirdness of the qubit case. But those who study contextuality know that there's all sorts of awkwardnesses that come from the case of even d is equal to 2, let alone d being even in general. It would be nice to be able to see what we can say about the case for qudits, to have a grip on how to approach these calculi, how to progress with an understanding of these, having a good framework of what are the things that we can do for arbitrary dimensions, arbitrary finite dimensions in any case. And I know that some of you are on board with that program, but from a theoretical standpoint, that seems pretty important to me. Okay, so synopsis of what our results are. We consider ZX and ZH diagrams on qudits of some arbitrary dimension, d greater than 1. So we make no assumptions at all on what d is. Some of our results will involve a little bit of case analysis, in particular in the case analysis of d even versus d odd, or we'll occasionally make conditions such as some parameter being a multiplicative unit. Of course, the objective is to try to make that assumption as few times as possible in order to get results which are as general as possible. We try to come up with retunings of the semantics for the generators of the ZX and ZH generators, which can be motivated specifically through discrete integrals, a concept that we sort of came across in other work that actually allows us to simplify the presentation of the generators. Now, what a discrete integral consists of is something along these lines, where you can define the semantics of a dot in terms of something that looks like an integral and in a technical sense is an integral. But the range of integration, the variable over which we're integrating, is an element of a finite set. There, I've not written a corresponding d mu. This is nor a dx. This is just a question of shorthand and a fairly conventional one for people who work with non-standard, uncommon integrals, let us say. Integrals with unusual measures. We can think of the index set d as imposing a type, and we will deal with a measure which is consistent every time we integrate over that type. And then we can express such things as the so-called Hadamard with d-dimensional qudits in general. That's actually more generally the QFT, the discrete the discrete Fourier transform. And we can express it simply as a double integral with an amplitude function with these double ket k and double ket x. Double ket k and double bra x. You might wonder what these are. This is a new notation. This is a slightly different thing than just a normal ket or a bra, but it's a closely related thing. These correspond to point mass functions. So d here, square brackets d, is the finite set of the basis state levels for our qudits of dimension d. It's a suggestive notation. You might suppose that this index set square brackets d is 0, 1, 2, all the way up to d minus 1. And for much of our work, you are safe in making that assumption, or at least that assumption is not harmful. I'll make some remarks on why you might want to choose differently. In any case, I'll describe what the double kets and the double bras are and what they are for and what they are doing. But this is how simply you can express the semantics. And in the case of d is equal to 2, these are precisely the well-tempered semantics for the white dot and for the Hadamard gate, or sort of in a very similar way, a decree to h box with amplitude minus 1. So these powers of nu, which were necessary to define the well-tempered semantics, those powers of nu have gone away. And where they have gone, they've been subsumed into the normalizations of the double kets, the double kets and bras, and into the measure by which we define the integral. All these details I'll describe in a moment. But this allows us to rederive the well-tempered semantics in a somewhat more straightforward way than originally was done. And in particular, it allows us to generalize these well-tempered semantics to arbitrary finite dimension greater than 1. For a second bit of synopsis, we take the opportunity to consider some other notational conventions for diagrams. Originally in this work, we hoped that we might be able to quickly express something about discrete integrals, about how these would be useful for simplifying the way that we denote well-tempered semantics and extending it, just to, sort of in 2 weeks, quickly get something out. But then it came to light that in order to demonstrate how these semantics were useful, in order to show that it did many of the things that you might hope, we needed to have a number of examples. And in order to contend with these examples, we had to find ways to express these examples. And as those of you who work with qudits know, things can get pretty awkward if you don't have some nice conventions to deal with them. So we ended up having to come up with a number of other conventions in order to help us to express these results. So one of the conventions that we do, this is a slight generalization of what Harney often does when dealing with qudits. Rather than having a simple amplitude, a simple phase attached to his green dots, Harney usually has a vector of coefficients describing what happens for the relative phases for each of the components of a green dot, and then similarly for, I guess in some cases, similarly for a red dot. I don't remember precisely, but certainly for the green dots. We found it useful to generalize this concept from a vector. We might as well express it as a function, and that allows us to express our results more uniformly for arbitrary dimensions. But we can just think of the metadata associated with a green dot, or for that matter, with an H box or a red dot, we can think of them as amplitude functions. And then we can define shorthand when these amplitude functions are a power of a single amplitude, or when that amplitude function is a phase function described by multiples of a single fixed phase parameter, such as what we would have for qubits, all in a way so that these conventions simplify to precisely the well-tempered semantics when we're dealing with the special case of qubits. So extending the convention in order to describe what happens with amplitudes, but providing shorthand in order to allow us to express things more simply when we're dealing with simple subcases. So what that would look like, you might have, instead of a single phase parameter lowercase theta, you might define a function, capital theta, from the integers to the complex numbers. And instead of having a single amplitude alpha for an H box, you might define an amplitude function from the integers to the complex numbers. We're thinking of the index set of the qudit just as a subset of the integers. And then you would define green dots and H boxes in this way. In the case of a green dot, where with the standard semantics, you have a simple sum of, let us say, relative phases defined by a coefficient vector. Here we have a single integral with relative amplitudes defined by this amplitude function. And if you want this amplitude function just to be a collection of relative phases, that's fine. That's a special case that you can consider. In the case for H boxes, we do the same thing. We have an integral over each of the indices. Now I have there x and y ranging over d to the m and d to the n. You can think of these, of course, as vectors where the individual wires correspond to individual indices within the x and the y, but you have an integral over these many indices. You take their integer product, and then you evaluate your amplitude function on that integer product. And this defines the entries of your matrix for your H box. How this pans out in practice, I will show in the talk. But this is how you could approach defining the semantics. That gives you more versatility by describing your amplitudes fairly generally. Pardon. And then I've got some other possibly controversial suggestions. You can judge whether or not they're good ideas or not, but which I can go into detail later on in the talk. Now, what this talk is really about, it's not just these individual tricks that you can do to simplify things. The meta narrative of this is that when we're considering how to extend ZX and ZH calculi to higher dimensions, we're going to encounter more complications simply because we're working in a more complicated regime. And we have to consider ways that we might want to try to change our approach to semantics in order to make it as easy as possible for us to investigate and then possibly in application use these different calculi. So some of the details of these calculi will inevitably depend on the particular dimension of D. That's simply going to be a fact. There are going to be differences between D composite and D prime. There's going to be differences between D is equal to 5 and D is equal to 7. That's fine. We're just trying to come up with ideas of what are the things which hold most generally. And then if there are particular dimensions which are of interest, one can try to investigate what is special to those dimensions or to special subcase, like perhaps there's something that you can prove if D is a square-free integer, an integer that can only be divided by a square if that square is equal to 1. That's something which is relevant to number theory. It won't be important to the talk, but it's something that somebody might have to consider at some point. We try to identify those results and conventions which are useful and which hold for all finite dimensions. The ones that, most importantly to me at least, reduce the clutter in order to reduce the number of things that you have to consider while reasoning in a scalar exact manner, or for that matter, in order to come up with a simple way of how various amplitudes combine. For example, in the stabiliser regime for the qudit case of ZX. And also, that simplify both for ZX and ZH separately, if you want to consider one calculus versus a different one without thinking about the other, or that allows you to use them together. If, like me, you hope to have a single tool that you can use that allows you to use whatever tricks you have in your bag. And of course, we want rewrites which are always sound, but specifically always sound whatever the dimension is. Now, that's all well and good. Part of it is founded on this notion of a discrete integral, which, in fairness, you might think is almost a contradiction in terms. What does a discrete integral then actually consist of? Well, this requires us to just dabble our toes a little bit in measure theory. And I mean it, we don't actually need very much measure theory at all. We just need to realize that the notion of a measure is general enough to allow us to find interesting things or meaningful things over finite sets. So a measure, so to speak, is just some function mu from a set of things that you think of as open sets. What these open sets consist of is can vary from application to application, but for any open set, defined from a set of open sets, which you describe as the set of open sets for which you have a defined measure. And then mu simply assigns it that measure. The measure can be finite. It's expressed as reals union infinity. You can have an infinite measure. So for example, in the standard way of thinking about measures, you would think of the entire real number line as a set that has a measure, and the entire real number line has a measure of infinity. In the meanwhile, the interval from 0 to 1 simply has a measure of 1. And any sort of continuous integral, whether it's open, closed, or half open, half closed, will have a measure precisely equal to its conventional length. But you can define measures in more general ways as well. And all you need is for this set sigma, this sort of set of measurable sets, it has to be closed under complements, and it has to be closed under countable unions. So for example, finite unions. And so in particular, you can define a set of measurable sets on a finite set. And so you can take a finite set. In this case, we're considering a finite set of D elements, the index set for our qudits. You could think of this in this case as the set of integers from 0, 1 up to D minus 1, if you like. But you can just think of the subsets of that set. All subsets of that set, you could define these to be the set of your measurable sets. And then your notion of measure simply has to be additive on disjoint sets when you take unions of disjoint sets, countable ones anyway. So it's fairly simple. I hope that this is not intimidating, because this is meant to be simple. Just think of like almost the most naive thing that you want out of a notion of bigness of a set. Now you have to be careful that you don't try to be so ambitious with your notion of bigness of a set that you might end up with contradictions. And when you're dealing with the real numbers, that's a concern. Depending on your axioms of set theory, you may be guaranteed to have unmeasurable sets. But if you're living in finite land, as we very frequently do, you don't really have to worry about that. You can just take measures which are straightforward relatives of the number of elements in a set, the cardinality. That's what we will do with our notion of a discrete measure. Okay, so given the notion of a discrete measure, what does it mean to integrate over a finite set? To integrate over a finite set is then just to take a sum with a weighting defined by the measure. So this is something that you might think of doing. This is a way that you can think about probability distributions, among other things. That's not what we're doing here, but when you think of such things as expectations over a random variable over a discrete set, implicitly what you're doing is integrating with respect to a measure, where the measure is the probability distribution. This is just a generalization of that. And we're actually going to take a very, very simple distribution, not a probability distribution, not something that necessarily sums to 1. So here's how you define it, that the integral of some function f of x with respect to x and with respect to a specific measure on the set is just the sum of f of x weighted by the measure of the particular element x. This particular formula doesn't work very well when generalizing to the reals, but we're not generalizing to the reals here. We're just dealing with finite sets. And so we don't need to worry about anything very awkward happening as far as that goes. What we will do is we'll consider a measure which is just the cardinality times some constant weight value, which describes the weight or the mass, if you like, of a singleton. Don't think of mass too seriously. I'm just trying to come up with evocative terms, but just the cardinality of the set times some weight value for each individual element, which is constant over all elements of here the set brackets D that we're considering. We're dealing with nu squared. For nu some positive number, why we're taking the square of it? Well, for a simple technical reason that we'll see in a moment. So we define this measure, and depending on the value of nu, we get different measures. It allows us some freedom to try to massage scalar values by defining the measure in a way which is suitable to us. Now, having defined this for some parameter nu, it will be useful to us also to define point mass distributions. And this is where the double kets come in. The double kets essentially represent point mass functions. They are, strictly speaking, basis vectors, but they're not usually orthonormal basis vectors. In particular, they're an orthonormal basis if and only if nu is equal to 1. But we're not fixing nu equal to 1. That's a choice you can make, but it's not necessarily one that we will take. We denote it by a double ket just to separate it from the usual single ket. So we can think of the single kets as the usual standard basis vectors that we know and love in order to help us describe how these things relate to our standard notation. The reason for defining these double kets is in order to obtain some of the benefits that we get from Dirac delta-like distributions over the reals to get analogous results for discrete integrals. So, for example, having defined this double ket with a normalization which is related to the normalization of the measure mu, we end up with this expression for an integral. We can take an integral of f of x, and you might think of this as saying, describing some wave function, the integral of f of x times ket x, ignoring the bra z for a moment. And then that would be a wave function, something you might describe as ket f. If you apply the functional double bra z to that functional, this selects just the coefficient f of z. And in particular, it selects precisely the coefficient f of z. It selects that value without adjustments to the normalization. This is the reason why we consider these double bras, and the reason why we define the measure in terms of the square of this parameter nu, so that we can consider 1 over nu as the so-called mass of these point mass distributions. Okay, so we have this notion of discrete integration, and here it is again on the upper left. We have an integral over a finite set with respect to a measure, which just is a renormalized version of cardinality. And we express this on the right precisely that it's a rescaled version of, well, a weighting, related to cardinality, but a weighting of the various values of f of x according to that normalization value. These discrete integrals allow us to automatically rescale any operator. That is to say, if we have a fixed denotation for an operator with these discrete integrals, and then we change the value of nu, this allows us to tune the scalar factor that would be involved if we re-expressed it in standard notation, in standard summation with single kets and single bras. The point mass functions allow us to simplify the analysis of compositions of these operators, simply by having a counterbalancing factor relative to the measure function for these elements x. So a way that you can see that this is going in the right direction is that by combining these two things, I've already shown how you can extract coefficients. We could also get nice representations of simple things that one knows and loves from physics or is useful for analysis of expressions, representing operators such as the identity through so-called resolutions of the identity. We can express the identity operator here as just the integral over double ket x, double bra x, over all x with respect to this measure. And this equality holds regardless of what the value of nu is, precisely because we've chosen the mass of these double kets and double bras so that all cancels. So we can get some freedom to retune the normalizations of our operators while having some very useful pieces of analysis remaining constant for all values of this parameter nu. Okay, so that's the central idea. What's the benefit of it? So this almost automatically gives you a recipe for interacting bialgebras. So suppose you've got something that looks a bit like this as a copy operator, and it's just the integral of taking a double bra x for taking a single input, double ket x to the tensor power n. Now you've got a scalar factor for each copy of double ket x there. So we've got a single integral, but we've got a power of 1 on nu there, which is implicitly 1 on nu to the n plus 1. We don't have to see this power there, but just to say that if you wanted to re-express this in terms of single kets and bras, you'd be dealing with a factor of 1 on nu for every single one of the indices there. And then you'd have some power of nu squared to deal with the fact that you're integrating over a single variable with respect to this measure mu. But in any case, we can write it like this. Here I've suppressed the dx or the d mu x for the sake of reducing clutter. And with the understanding that we're working just with this measure, we don't have to keep talking about that measure all the time. Suppose that you also have semantics that allows the state double ket 0, not ket 0, but double ket 0, to be denoted by a red dot. Now, this isn't a sort of basis, this isn't a basis equivalent way of sort of constructing the semantics for double ket 0, but never mind that for now, we'll get into that. Supposing that you had semantics for which you had both of these equations. Then composing them, you would simply compose the integrals. In the same, if you were working with operators expressed in terms of sum, you'd compose the operators in the same way, the sums of the two operators. You end up with a double bracket x0 that will essentially pick out the one entry of the integral in which x is equal to 0. And so we get double ket 0 tensor n. And what diagram is that? That's that diagram. So we see that, wandering through this, explicitly addressing the semantics in terms of these discrete integrals, immediately gives us the sort of result that we might like if we were looking for well-tempered semantics. And this equality is independent of the dimension. It's independent of the particular choice of nu. It's just very fluid and convenient. So these discrete measures with an accompanying set of point mass functions, which are defined with respect to that measure, they automatically produce Frobenius bialgebras. That comes for free, essentially through the mechanics of how you work with composing these and simplifying the integrals. Now, it's important to note that this is a specific normalization. So this is not talking about how diagrams representing states are transformed. These will, in point of fact, be super normalized for the normalization that I would like to consider, but that's no different from the standard semantics, which is also super normalized. You can't get everything for free, but this is represented about as simply as possible. It is not a scalar times some simple bit of notation. It is just the point mass function itself, perhaps raised to an appropriate power. And then if you want to consider how this caches down to single kets and single bras, that is a step that you can take separately, seeing basically exactly how many copies of something you have. Okay, so these results hold for whatever the normalization is that you take for the measure, for whatever measure that you have, which is constant over the index sets D. Now, if you want to have a calculus that works for unitary circuit and complementary bases, you need more than this. You can't have some, this is, working with unitary circuits and avoiding scalar gadgets isn't something that's going to happen for all possible values of the measure. It's going to single out a very specific value of the measure. What we want to consider the semantics for the H box. So here's a description of an H box with an amplitude parameter omega. And this will give relative amplitudes of omega to the x1 times x2 up to xm times y1 times y2 up to yn, where x and y are the vectors of indices for the inputs and outputs. And in particular, that's an integer product up in the exponent. But if you take omega to be a primitive dth root of unity, that multiplication happens to be well-defined modulo d. That's something that will be useful to us later. We'll see the ramifications of that. Those ramifications are going to be surprising. Among other things, Roy has already considered that in his PhD thesis. But this is how we would denote an H box with a parameter omega, an amplitude parameter omega, and for this particular value of omega, it gives rise to a generalized controlled Z gate. Now, without getting into the details of this, there's a single sort of, maybe not sort of unique way that you can generalize the controlled Z gate, but there's a way that you can generalize the controlled Z gate, in which a number of the nice sort of number theoretical properties hold that you might want to use. And so this particular notational convention reproduces that directly. This is how you would denote a generalized controlled Z gate. So what it's generalizing, it's an integer controlled gate, where what it's controlling is a generalized Pauli Z gate from the natural way that you would generalize a unitary Z operator from qubits to qudits. So this is how you would express that. It's simply a double integral over these indices x and y, and with appropriate relative phases. Expressed in terms of sums, you get a bunch of canceling factors, again, because we've engineered the norms of these point mass functions with the double Ketz-Bros to cancel out against the measure. And so you get precisely the controlled Z gate if you denote this. So that simple representation of that well-liked unitary gate, that comes for free with this particular representation. But if we want to use H-boxes to denote such things as the quantum Fourier transform, a unitary operation on a single qudit, then we end up getting some constraints, constraints that fix a particular measure function mu, and thereby a particular value of the parameter nu. Okay, so if we take a gate such as this, and this is the semantics that you would get if you described it very simply in terms of discrete integrals, just a double integral with the relative phases, x at input, y at output. And this is how you'd represent that integral in terms of discrete sums. Here, all of the nu's don't cancel each other out, essentially because we have two integrals, but operating on a single qubit. If we want this operator to be unitary, then what we need is for nu squared to be equal to 1 on root d. And those of you who are quite familiar with the quantum Fourier transform on qudits will recognize that we would want that leading scalar factor to be 1 on root d. So this semantics denotes a unitary if and only if nu is equal to d to the negative 1/4 power, which may sound quite similar to what we've seen before with the well-tempered semantics. You could describe this as no accident. This is reproducing by more streamlined means the well-tempered semantics, but without the assumption that d is equal to 2. So the main results in terms of describing the benefits of discrete integrals, we reproduce and we extend the well-tempered semantics for ZX and ZH diagrams on qudits for any dimension greater than 1. You simply define a discrete measure on your basis state labels, just consisting of some weight function applied to the number of elements of the set for the set that you are taking the measure of. So for a singleton, the measure is nu squared. For the entire set D, it ends up being the integer d times nu squared. You define a basis of point mass functions. That basis is not orthonormalized, but they are orthogonal. They are orthogonal basis functions. And the normalization is tuned in such a way that you get very good interoperation with the integrals. By assigning semantics of the generators essentially as simply as you possibly can in terms of discrete integrals and point mass functions, and setting nu to be d to the negative 1/4, you obtain semantics which essentially extend the well-tempered semantics to arbitrary dimensions. And things work out very nicely. So what do these semantics look like for ZX generators? So here we have an amplitude function, theta, from the integers, of which the index set is a subset, but just from the integers to the complex numbers. And we simply use this to define the relative amplitudes in between the different components, the d different components in this operator, which we're describing by discrete integral. And you don't have to be mindful that this is exactly equivalent to a sum over d. You can rely on that if you like, or you can just get lost in the discrete integrals. And by lost, I don't mean bewildered. I mean, just sort of, if you have to deal with concrete semantics at all, just do all of your concrete semantics in terms of integrals. I think it worked out fairly nicely. For the red dots, you do similarly, only you do it for a Fourier basis. Now here, we're defining these vectors. These are just eigenvectors of the Pauli X operator, the shift operator in d dimensions. And here we're following the convention adopted by Booth and Corrette and also telegraphed by Ye and by Van de Wetering for qudits in particular. This is something that you could do in order to make your calculus flexisymmetric. We decided in the end that it was better to have calculus that was flexsymmetric than being precisely the same basis, or precisely the same basis without permutations on the Kets and the Bras. It makes some minor things in the calculus a little bit more complicated, but it makes the rest of it easier to work with. It's the sort of thing which is a consistent theme in working with arbitrary dimensions. If you make the right small compromise in one place, you save yourself a lot of headache in other places. And so this was a convention that we would like to advocate more generally, but pardon me. But yes, this is essentially just analogous to what Booth and Corrette have done, and sort of a natural generalization of what you do for qudits. For qubits. For qubits, actually, the minus sign in the K doesn't matter, simply because you end up with -1 being equivalent to 1 modulo 2. For reasons of sort of choice of presentations, it's not essential. We prefer to define generators for both the Q of T and its inverse. Just these two operators. You can see that they're just different by a minus sign in the exponent. We've chosen to denote them by a plus in the box and a minus in the box. Just as simple as that. The rewrites that we get fusion rules that look like this. So here we're dealing with amplitude functions. We get a usual fusion rule-like thing, only we have pointwise multiplication of the values of these functions evaluated at the basis states. If you want to consider phase angles instead in the shorthand, where you're considering an amplitude function, which is just various powers of a fixed relative phase, then you would express that similarly here. So with that shorthand, this simply reproduces the familiar rule that you have for qubits. Color change rule, you have something that looks like this. Note that it's the Fourier, the plus H box, both on the input wires and on the output wires. This is something we saw with Booth and Corrette as well. Just so that you don't have to think about whether you have inverses on some wires and non-inverses on the other wires. Bialgebra style rules, we get bialgebra rules which are as nice as you could possibly like. We get a multi-edged hop rule that looks like this, no additional scalar gadgets. And we get an antipode rule that looks like this, where we have a single degree 2 red dot, which is playing a role of an antipode, which is something that I can comment on later a little bit if there's time and interest. And we get a nice feature that there are a lot of simple scalar gadgets that just represent the empty diagram, that is to say the scalar 1. And so on. There's a number of things that you could say, but these are sort of the highlights. The notation for stabilizer ZX for stabilizer ZX, I guess I should say, stabilizer ZX is an interesting special case to many of us, particularly those who want to think about generalizations of simulation results or error corrections. There's an awkwardness that arises when trying to deal with the stabilizer formalism, in that it becomes very important whether or not your dimension is even or odd. And like there are other things where it matters whether or not it's composite or prime, but I think the most important distinction is whether it's even or odd. Now, there's a question, how can you do something which is uniform over even and odd cases? This is a question that I've contended with before myself. So you isolate a particular root of unity, tau, which has this particular formula. It's not going to be important for you to memorize this formula, but this is a particular root of unity. Why this particular root of unity? This is something that we will use to try to smooth over the differences between even and odd. This scalar has something in common. It captures something of the difference between what happens with the Pauli operators when D is even and when D is odd. So no matter the dimension, this tau is chosen so that tau squared is equal to omega, which is our usual primitive root of unity, e to the 2 pi I on D. So if you're happy dealing with omega, just think of tau as a very specially chosen square root of omega, but it's not necessarily a primitive square root of omega. That will depend on the dimension. The generalization of the Pauli operators that you use for arbitrary dimensions, You have an X operator, which is a shift operator. It shifts all basis elements modulo D by 1. And you have a Z operator, sometimes called a clock operator, which simply has the standard basis as an eigenbasis and gives an eigenvalue of omega to the t when you put in ket t as input. These are the generalized Pauli operators. Now, you might think of what's the generalization of the Y operator. The Y operator is sort of sad and unloved, even in the qubit case, because it involves an imaginary number in its description in terms of Z and X. It's a bit unfair, and it's sort of important to recognize the role of it. And in particular, if you want to consider what happens with qudits, you have to think of what the natural analog is of the Y operator. There's not going to be a single unique thing, which is the analog of the Y operator, but something that you might do is choose Y to be something in terms of X dagger, Z dagger, so that you can make statements about what the product of X, Y, Z is, that generalized from qubits. If you define Y to be equal to, if you choose Y to be proportional to X dagger, Z dagger, and you're not careful, you might not get something which has the same properties as X dagger and Z dagger, so X and Z. X has order D. If you raise X to the power of D, you get the identity operator. Similarly, Z has order D. If you raise Z to the power of D, you'll get, again, the identity operator. If you were to choose Y to be equal to X dagger, Z dagger, for instance, then Y would have order D if and only if D is odd. And otherwise, it would have order 2D, which is a bit awkward. But you can finesse this by prefacing it by a scalar tau, where tau is defined as there. And in the case where D is equal to 2, tau is precisely I, so that this gives the description of X, Y, and Z's relation in the standard presentation over qubits. So this is something which is, I guess, a patch that you can use in order to try to smooth over the differences that you see between even and odd dimensions in the stabilizer formalism. And this doesn't bridge all the differences that you would see, but it bridges over a great many of them. And so, you simply use this convention of this scalar tau and thinking about defining the stabilizer formalism over qudits in terms of this scalar tau. So in particular, we can take a square bracket notation. This is, again, this is a riff off of Booth and Carret's work, but we take A semicolon B in brackets. We use this as shorthand to denote an amplitude function evaluated over the integers, which is just a particular power of tau, a power of tau which is potentially a quadratic function in X, the basis label. And so we have 2 times AX, why 2 times AX? Well, that way we will have something to do with tau squared for things which are very much like the Pauli operators. And then we'll have this separate quadratic component to B times X squared. And A and B in principle can be any integers that you like. In many cases, you'll be able to think of them as being evaluated mod D. That's fine. But yeah, with such a convention, you can define green and red quadratic or stabilizer dots like this with discrete integrals. You can generalize this straightforwardly for multiple inputs, multiple outputs, or degree 0 dots. And you can let, if B happens to be equal to 0, you can simply omit it. If you do that, and you also use the discrete integral notation, you get this representation for double ket A. So this isn't precisely the notation what we used for double ket 0 when we were talking about Frobenius algebras, but it's very close, and we can actually show that without that second red dot, without that second antipode, you would still have double ket 0. You get simple representations for the Pauli operators. There, with these integrals, we're dealing again with the fact that tau squared is equal to omega. So these are simply describing the Z and X operators in terms of their eigenbases. This generalizes if in the square brackets 1, instead you had square brackets A, you would have Z to the power of A or X to the power of A. There's another important operator that you need to generalize the stabilizer formalism. It's a sort of an X squared operator. You can define it simply like this. And if you have a degree 0 dot, and if B happens to be a multiplicative unit modulo D, then this degree 0 dot will be equal to just a complex phase. The fine-tuning of the normalization, the choice of the measure, happens to be such that these will frequently become simply global phases. That gamma will depend in principle on A, on B, and also on D, but this is just to express that they would simply be complex phases. And this would, in practice, serve to simplify a lot of rewrites, I think. Now, so there's a question of like, how it is that this has come about. This actually took me very much by surprise. I didn't see this happening at all. I didn't foresee this happening at all. It's quite possible that, this result comes from the analysis of Gauss sums. I am not an expert in number theory enough to know a lot about Gauss sums, but it seems to me likely that the results of Gauss sums have come through working with Fourier analysis. And so it's possible that this is not a coincidence, but something from a common cause, something from just choosing to approach the representation of the Fourier transform in a particular way has given us something that involves the Fourier transform being represented simply. For ZH generators, the semantics that we have, well, we get as generators, semantics which are as simple as possible for the white dot. It's just a simple integral over x of double bra x, double ket x with appropriate tensor powers. We have, for H boxes, we have this with amplitude functions. So we have got an integral of the appropriate degree. We've got some product of all of the index values, x1 up through yn. Then we take the value of that integer product and we evaluate our amplitude function on that. Yeah, so again, it's stressing because this is an important technical point. We consider these as products of integers, not of integers modulo d, but integers. Again, we prefer to define generators which generalize the not dot and the gray dot instead of thinking of them as being derived through particular structures. So we define the not dot this way, parameterized by some integer c, where that expression is evaluated modulo d. All the expressions within the kets and the bras, or the double kets and double bras, those are evaluated modulo d, but only there. Yes, so with that particular convention, this also follows Roy in the way that they defined the generalized not dots. And we have gray dots defined this way, where that sum in that double bracket is also evaluated modulo d. And it's a way of imposing a constraint on the sum of the index labels. You could also express this as a constraint on the limits of the integral. It doesn't make a difference which way you approach it. I happen to prefer to describe it this way in order to consistently leverage the benefits of having brackets with the point mass functions defined as we have. Now, there's a corresponding special case in ZX to the stabilizer case. It's a so-called multi-character case. I don't know if this had a name previously. I'm happy to be told about it, but for the lack of knowledge of a different name for it, I'm describing it as a multi-character regime. So a character is just a group homomorphism from some group, in this case, we'll have in mind the integers, but from some group to the multiplicative complex numbers. A multi-character function is a function like this, where you just have many copies of that group, additive copies, if you like, direct products of that group, again, to the complex units. And it's homomorphism in each factor of the group product separately. So one that you might be interested in considering is something that maps a pair of integers to e to the 2 pi I times some constant times the product of the two integers x and y. So essentially some power of omega is what we're talking about, governed by the two inputs and some auxiliary parameter c. So as an amplitude function, as an h box described by an amplitude function, you would write it this way, just as an h box with eta sub c. But because this function just describes powers of a common amplitude value, we can denote it in a different way. So this is how we would write the semantics for this. They're just expanding the definition of this function, eta sub c, within the double integrals. So describing it as a function, because it's just describing something which is powers of some particular amplitude, we can describe it as, what happens when you take products of powers of a fixed amplitude omega to the c. C might happen to be 0, in which case you're taking powers of 1. That's neither here nor there. That's something you could do if you want to. But yeah, powers of some fixed amplitude. But it will be useful, again, to decrease clutter as much as possible, to consider a notation for this specific case in which we think of the C is actually all the information that we care about here, where we take this index C and we put it within the box. So this is a significant departure from the notation that you would see in the original presentation of ZH by Alex and Miriam. But this is just a shorthand that we suggest might be a useful shorthand to use for just considering what happens in this particular subcase, this particular subcalculus of the ZH calculus. If we do that, then the H box with index parameter +1 is exactly equal to the QFT that we have from the ZX calculus. The -1 parameter gives us the inverse of the QFT. So again, as a way of bridging the two calculi and motivating the plus and the minus notation for Hadamard boxes with ZX. More generally, with an H box, if you have an H box with parameter C, an index parameter C, it's the same as what would happen if you have omega to the C as an amplitude parameter, and it just describes this integral. Okay, so much for that. This is just to describe what a multi-character H box is even, and how we often find it useful to write it for the sake of brevity. Now, what sort of rewrites do we get out of this? So we get fusion style rules as usual. Again, note the absence of scalars. I'm not sure, I don't recall whether you would expect to see scalars for the gray dots. You wouldn't expect to see scalars for the white dots anyhow. But in any case, you do have these rewrites without scalars. So yeah, in particular, the gray dots then are quasi-spiders. Harvestmen, I think, is one term is often used for that. If we define amplitude functions A and B, then we get a multiplication rule that looks like this for pointwise multiplication of the amplitude functions. If you have a collection of integer parameters like this, then you get, for example, this special case of that multiplication rule, just for the multi-character subset, where we get an addition of the indices. Essentially, the indices here act a bit like exponents in the amplitude functions, exponents of powers of omega. And you get not exactly a fusion rule, a sort of displacement rule for phase parameters for the not dots, a difference rule of sorts. And in particular, if you've got some parameters U and V, which are units modulo D, then you can have nice H-box fusion rules that look like this. And this holds for whatever the value of U is. In particular, if you want U to be equal to 1, this describes what you might like out of the simplest fusion rule, reproducing the sort of thing that you'd expect from the ZH calculus for qubits. Color change rules, you get ones which are as nice as possible, and it doesn't matter what the value of U is, so long as it's a multiplicative unit. You get that in both directions. So you don't have to worry about getting scalar gadgets depending on which direction you do the color change. And you can get a nice decomposition of the not dot. That strikes me as being a little bit like the Euler decomposition of the Hadamard gate in ZX. I don't know if there's anything to that analogy, but it's an analogy that, however superficial it might be, I like and would like to understand a little bit better. But anyhow, this is a nice decomposition of the not dot. You get bialgebra style rules, as nice as you like for white and gray. You get multi-edge rules that allow you to describe how to do what you might describe as a multiplier operator. So where you've got k edges there, k can be any integer. And then U being a unit, you have a way of describing such multi-edged gadgets between white and gray dots. You have a nice bialgebra rule between white dots and H boxes. Again, here U and V can be independent units. It suffices for U to be a multiplicative unit modulo D, and V for also to be a multiplicative unit modulo D. And then you can essentially move fluidly between units with this particular rule. If you prefer the mixed bialgebra rule, then you can use this, but then you have to keep the same unit on both sides of the equation. But that one ends up coming out nicely as well. Again, no scalar gadgets involved, and so forth. So compatibility between these calculi. So what does it mean for these two calculi to be compatible? I've described what happens with ZX diagrams and ZH diagrams. And you might wonder, well, if they're both, what I've described is no ambitions to be universal. It's not even universal, so far as I know. But you could imagine in some extensions which would be universal, in which case you might ask, well, why would you care about them being interoperating? If you've got one calculus, why would you worry about the other? And it's a soft target, like it's a soft objective, I should say, that there are different perspectives on the same calculus. There are different perspectives on the same calculus because we have defined them carefully so that you can easily translate one to the other without having to worry about arities too much in scalar gadgets. They allow you to take different perspectives on the same sort of diagram. It's essentially the same reason why you like to have theorems rather than always working from axioms. Different ways of summarizing transformations give you shortcuts that allow you to be as effective as possible in analyzing a diagram. So I'm not trying to define what compatibility is, but I'm trying to suggest what the point is, that we have some overlap in the semantics of some of the generators. So for example, on the upper left with the white and gray being comparable to the green and the red, essentially just a simple color change gives you an equivalence. And some simple diagrams are easily translated, such as we have with the bottom left, where a green theta dot can easily be described in terms of something with white ZH dot with an H box with the same amplitude function theta. That's a good motivation for having something which unifies how you parameterize these things. By having amplitude functions for both, you can more easily just describe how that specifies something else in a different diagram, in a different denotation. But you can see that we get simple ways of describing things. And on the right-hand side, we have a number of things to do with scalar gadgets. We've got ways that you can describe certain scalar gadgets explicitly. A green dot with no parameters is explicitly an H box with amplitude square root of d. It represents a scalar of square root of d. Why square root of d? Well, that just has to do with the measure. On the other hand, a green dot with theta can be used to express an integral, a scalar which consists of the integral of theta with respect to all x, if that's something that is important to you. Anyhow, so we get some nice translations between simple diagrams. Not all diagrams will translate very simply. That's the point of the sort of Fourier analysis distinction between ZX and ZH. That was sort of highlighted by Alex and John and others, who's the complete author list, which I don't remember. Apologies for that. But there's some common ground that allows you to move fluidly between the two when it would be most useful to, I think. The features of a ZX calculus, a unified calculus, is that you don't have a complete equivalence between multi-characters in ZH and the Clifford hierarchy for ZX, but you do have some relationships. So for example, if you want to consider powers of powers of the controlled NOT gate or the controlled addition gate, and powers of the controlled Z gate, you can express this very easily with ZH, just using the fact that their H boxes are closely related to multipliers. And if you want to have multiply controlled Z gates, again, you just have this very nice relationship to multi-characters with ZH diagrams. Similarly for controlled NOT operators and so on. So it's grounded on the fact that these H boxes in the multi-character regime are it sort of breaks down what you might call a multiplier, a sort of simple example of scalable ZX notation, which just multiplies all of the elements of the index space by some constant C. And so it's a way of relating some of the things that you have in the ZX stabilizer case to the multi-character case. Of course, it allows you also to generalize the NOT dots from ZH by identifying that they're equivalent to red dots of ZX, which are not so limited in being ranging over discrete value. And you get more transparent scalar gadgets as well. When you do have to deal with scalar gadgets because you're representing phases, instead of having some sort of knobbly thing on the left, you can just say, well, this is the scalar corresponding to theta of C. So in summary, if you want to reason about ZX and ZH diagrams exactly, which is to say in a scalar exact way, and you want to do this somehow using semantics like the well-tempered semantics, but you want to have some way of motivating where those semantics come from, or you want to do it not just for qubits, but for arbitrary qudits, then discrete integrals allow you to define the semantics as simply as possible. You have to understand what the discrete integral is, or at least how to use it. But with just a little bit of groundwork, you get useful expressions such as this, which is about as simple as the standard semantics are. And it yields versions of the calculi which I think work well for stabilizer diagrams and for the multi-character regime in ZH. They should work well together, these versions of the ZX and ZH calculus. And most importantly, they avoid introducing scalar gadgets for what I think are the most common rewrites. That's a statement which is subjective and may depend on the particular application, but for the applications that I have so far seen, I think that this is a well-founded statement. All right, I haven't been keeping track of the time, but thank you for your time.
Thank you very much, Niel. Let's give a virtual round of applause. So I'm aware that it's the time is somewhat dragging on. I'm going to have to go fairly soon. This is just kind of a sanity check question. So because the Fourier transform ends up being unitary by virtue of the scalar coefficients, does this mean that if you put a plus spider or a plus box followed by a minus box, this is exactly equal to identity rather than just being up to a factor? Do you know?
Yes, precisely so. That's one of the motivations, of course.
Cool. I had another question, which was kind of you were talking a bit about how you had to develop quite a lot of this quite a lot of the syntax for some examples that you had in mind. Maybe without going too deep into it, what sorts of things did you have? What sort of applications do you have in mind for this kind of?
Well, I wasn't thinking about applications from the standpoint of using this in quantum information theory or in quantum software, except in some sort of generalized way. Basically, the applications that I had were sort of the analysis of the stabilizer special case of ZX and of the multi-character case of ZH, which I don't pretend to give a formal definition of it, but I think you probably could define it as the subcase of ZH consisting of any diagram where all of the H boxes simply have these indices, amplitudes which are powers of omega. So it was the fact that I could, so in order to exhibit examples of how the calculus worked in special cases such as that, these were the so-called applications that I had in mind, that at least with these special cases, it shouldn't be terrible to use.
Right, thanks. So in the odd stabilizer case, or sorry, if you have in the odd prime dimension stabilizer case, you have this relationship with Lagrangian algebra. So I think Cole, who's not here at the moment, has a paper with Alex about this. So do you know whether there's kind of a nice reduction? So like if you're in the odd prime dimension stabilizer case, and you plug in the appropriate new and so on, do you know if you get similar calculus to the Lagrangian algebra kind of calculus that
So I'm afraid the short answer to that is no, I don't know whether or not you get the same calculus. But I guess a question that I could ask in order to try to answer that is what features that calculus has derived from the Lagrangians? Does it differ, for example, from the standard semantics?
Well, I've just realized now actually that one of the main ways in which that differs is that the monoidal product it uses is the direct sum rather than the tensor product. So actually, I've realized that my question doesn't really make sense.
It could be that it could be massaged to make sense if you had some additional syntactic sugar to relate the square bracket notation, which is in principle a tuple. You could describe it, as sort of an extended notation of tuples to talk about things with multiple qubits. In which case, conceivably there could be a relation, but I simply cannot say.
Yeah, actually, again, I've just realized that it does become the tensor product, because the whole point is that you have the direct sum of Lagrangian subspaces, but then there's a functor from this to Hilbert spaces, which takes the direct sum to a tensor product. So anyway, maybe it does actually work out.
Yeah.
I can't remember it well enough. But
At least
yeah,
it's
awesome.
at least it's well typed at the image of the functor for the Lagrangian relations that that it's a question that makes sense to ask.
Yeah.
But I guess the question again is, what features do you expect of the image of that functor?
Yeah.
Like, so for example, the Fourier transform is their representation of the Fourier transform unitary. Do they have, what is the normalization for something that might correspond to an x dot, sort of a copy operator? That would be the most straightforward way to investigate that.
Yeah, I can't remember at all.
If I were to naively guess, just based on vibes of the research field, I would guess that it corresponds more closely to the standard semantics, but that's just an informed guess. I haven't had the time to read that paper.
Cool. Oh, so there's Robert's typing in the chat. He said Titwan and him gave a functor from the stabiliser qpit zx into affine Lagrangian relations over ZP, where you quotient by all non-zero scalars. Right. Yeah, so I think that's basically the same thing that we were talking about. Although does this functor also, I mean, I don't really want to go into all of the hairy details of this for the purpose of just this question, but does this functor work for all prime dimensions or just the odd prime dimensions? That is, the prime dimensions that don't include 2. Yeah, okay, cool. In which case, yeah, I think that will be basically exactly the same thing as what Cole and Alex talk about in their paper. Cool. Right. Are there any other questions from the field? Okay, I'm going to take that silence as, oh, we have a question from Robert who says, do you expect this to interface well with scalable ZX when considering the case D is a power of 2 to sorry, yeah, D is D equals 2 to the n?
Yes, I do. I don't have a big list of specific things that I'd want in mind, but the toy concept that I have is, how would I at least express Shor's algorithm? And Shor's algorithm involves sort of multiple modular exponentiation, which is to say multiplication by a scalar which is controlled, where the power of that scalar, or the number of times that you multiply a target register by a scalar, is itself controlled by an integer register. That's not all going to be something which you would do over a single qudit dimension, but it's something that you'd want at least to have some way of expressing just multiplying by a scalar or qudits of dimension d. And this is something which happens directly. Like, so for example, this, it directly allows you to denote multipliers by arbitrary constants modulo d on qudits of arbitrary dimension. Some of the, many of the times those won't be unitary if the parameters c involved. Let me scroll up to a relevant slide. Actually, I want something on, yeah, there we go. So these are the slides I want. So just this. What you'd want is essentially something like an integer controlled C arrow, where C happens to be a multiplicative unit modulo D. So like this allows you to very directly denote such a thing. That's like, I would describe that as the very first step to a scalable representation, a scalable ZX representation of something like Shor's algorithm. To do this with mixed qudit dimensions, when I say mixed qudit dimensions, I mean that to represent Shor's algorithm, you would want a controlled multiplier operator, where the multiplier operator is like that gray arrow in the middle, where the operand of the arrow itself would be of one dimension, and the control would have a different dimension. So this calculus doesn't describe how you would talk about that. That would be something you'd have to do in future work. But it's a start, at least.
Okay, Robert says he has one more question, which I'll read out when he's put it. He says, you've mentioned you're working on this with Richard in the past. Am I right in guessing that taking nu to be some kind of infinitesimal leads to the skeleton of an infinite dimensional version of the calculus?
I didn't understand precisely what was meant by that, but this is related to work with. It was a spin-off of some of the observations that we made working with the infinitesimal calculus. To come up with an infinitesimal calculus of the sort that we think would be helpful, it doesn't suffice simply to take d to infinity. Something similar to that is something that you might like to do. If you think about what would happen if you took d to infinity with this calculus and just ran with that, what you'd have is you'd have this measure that we've been considering, and the measure of a singleton set is nu squared, where nu is d to the negative 1 on 4, so that nu squared is 1 on the square root of d. So as d goes off to infinity, the measure of a singleton element in this set goes to 0. And meanwhile, the measure of the entire set goes off to infinity. And so you get something that would represent a sort of a Riemann sum. The question is whether the Riemann sum will do all the things that you hope for it to do, and under what conditions it would do all the things that you'd hope for it to do. It's our belief that it's not enough to just take d going off to infinity, but some interesting things will surely happen if you take d going off to infinity. And the question is whether those things would be all that you hope for.
Cool. Okay, thank you very much. I think it's probably a good time to wrap it up there. So thank you very much for presenting, Niel, once again. I don't think I have a speaker